we're going to skip a fair amount of stuff. We have skipped a lot of chapter 3, most all of it. I talked a little bit about the some stuff from section 2, and then I was going to do some things in section 3, and I spent about an hour and a half working on that. Just then it got to the point where I said, you know, I can't explain that properly. That's a good section for getting some idea as to what you can do with differential equations, with the linear differential equations. We're a little bit behind where I hope to be, so I thought let's go on and get into chapter 4, and there's some stuff at the end of chapter 3 more on approximations, improved Euler method, and something called a Runge-Kutta approximation method. We may come back and do that because Runge-Kutta is pretty nice thing here. But what we're looking at now is we're going to be looking at what's called a spring mass damper system. Okay. And I need to find my notes here. Okay, so what we have here, and this is a picture that's very similar to what's in the book. It's not exactly what's in the book, but we have a spring, and on this picture here I've got K in front of it, which I'll talk about. We have a mass, which is a box, and it's on wheels. Okay, and the idea is that if we have this mass displaces the spring a certain amount, I mean, it's not at rest. If we like pull it out some and then let go of it, then it's going to start to move, and the spring is going to make it want to oscillate. The bottom we have wheels, and there's a B there. The idea here is that these wheels are not perfectly frictionless. In other words, they're going to supply a little bit of resistance to the motion. And the equation we're going to be working with, y of t, has to do with the displacement, or the position along here. Now, I've worked, most books I've looked at have called this as the spring. It's a spring mass damper system. And most of the books I've looked at have done this way. We have the spring, and that's kind of a beautiful looking spring. Hanging on the end of that spring is some mass. And if you just give this thing a push up, or you pull it down a certain amount and let it go, it's going to want to oscillate back and forth. Okay. Now, a damper would be something which lots of times is drawn this way. Okay. It's just something that's going to provide some resistance, and like a shock absorber, like a hydraulic shock absorber. As this goes up and down, well, you've got some sort of piston here, and maybe it's some sort of fluid, and it's going to provide some resistance to it. And I've drawn better pictures than that, but I like the picture I've drawn, even though it's pretty pitiful. I like it a little better than the one that the book has, one I have like up in the upper left corner. There's an example we'll do later on, which, well, it's a sliding block problem, and it's a little more to it than I don't like that picture. Let's just say I don't like that picture. So I'll use it, but I prefer my spring mass with some sort of damper. And as this goes up and down, this piston will have to slow things down. Okay, so we're going to do some physics here. Let's start by recalling Newton's second law. It says force equals mass times acceleration. Well, mass we got. It's m there, and the acceleration is always the second derivative of the position. So in other words, m times y double prime. That's the force. Okay. Now, there are other forces. I mean, this is the total force here. We've got to figure out what the equation is for y is what we're after. But there are other. This force is made up of several different things. Okay. One of them has to do with the spring that we've got there. And Hooke's law is something that you may or may not recall from physics or whatever. I did it just a couple of weeks, about a week or so ago in college algebra. And what Hooke's law says is the force needed to stretch or compress a spring is directly proportional to the displacement from the equilibrium position. So as far as the spring is concerned, we have a force here. We'll call that force from the spring. And that's going to be, okay, directly proportional means constant times y, the position, the displacement of this thing here. Okay, and that's a negative because the force that the spring is going to exert is going to be the opposite direction of however it's stretched. If you're stretched to the right, it's going to want to pull you back to the left. If you're compressed to the left, it's going to want to push you off to the right. Now this K is called the spring constant. K is a positive constant. Called a Springs constant or the Hooke's constant. This book used a term I hadn't thought of before, but it's a pretty good one. They call it the stiffness of the spring. Now, of course, if you pull the spring too far, then the spring becomes sprung, and what you've actually done is rearrange the molecules in it, and it's a different spring, so you have a brand new constant. But as long as you don't push it, compress it too much, or pull it, stretch it out too much, then this particular constant will be a function of what the size of the spring, the thickness, how tightly wound it is with material, and so on. Okay, so that's Hooke's law. So that's one. We're going to have our total force up here, and this is part of it. It's what the spring is going to be supplying. Okay, that's part of it. So the force of the spring is negative K times Y. Now we have a damping force. With the picture we have here, the damping force is perhaps the wheels don't turn real well, or just the fact that there are wheels there are going to make it. It's going to take a little more to move them than it would be naturally. So it could be friction. It could be, well, it could be like we have a piston type shock absorber like cars and trucks have on there. But this damping force is going to be a function of how fast it's moving. In other words, if the the faster the object moves, the more damping there is. Okay, so generally, how we would express that is it's generally proportional to the velocity. Okay, so that would be the force, and I'll just call it damping, which the book calls friction, but it isn't necessarily friction. That's going to be and it too is going to operate in the opposite direction of motion. So if we're moving to the left, then the damping force is going to want to push us. When it slows us down, it's going to push toward the right. If we're moving to the left, well, if we're moving to the right, it's going to be the other way. So that's why it's minus B times F. So B is our damping constant here as well. Okay, and you may also have some sort of outside force. Okay, and I don't know what it's going to be. It can be any number of things. I'll give you some examples as we go along here, but it's going to be a function of T, and I sometimes don't write that down, but it's the external force. So it could be that we set up one of these systems on the tabletop, and the process of motion is going to make the table vibrate, and that will interfere with the motion. Or it might be something like, I remember when I was in school, if we'd get on the school bus, we'd try to get the very back end of the school bus. Okay, and of course it would have a natural sort of vibration on the springs on that, and we'd try to jump up and down in the back of the school bus and try to. Somebody said if everybody got to the very back of the school bus and jumped up and down at the right frequency, then we could actually get the wheels to bounce off the road. But anyway, but that would be an outside force, something else acting on it. Okay. Now let me give you. Okay, so let's see. We'll do that. I'll uncover the right-hand side in a minute. So putting all of this together, okay, we have that the total force is mass times acceleration. It's going to be the sum of all the other forces. It's the force from the spring, the force from the damping, plus the external force. So that's our equation of motion we're going to try to solve. Let me rewrite it a little bit then. Is m times y double prime plus b times y prime plus k times y is the external force. If you just bring those spring stuff all over on one side and let the external stuff be by itself, we have this equation. Okay. Okay, so what we're going to do is we're going to examine two special cases of this. Let's suppose that we don't have any damping. So we're moving on a frictionless surface, or we're probably the better thing to think of it is we're going up and down. There's nothing, we just have a weight suspended on a spring. There's nothing slowing it down. And let's also assume that there's no external forces acting on this. So the equation then would be the my double prime plus ky equals 0. Okay. Now, I didn't leave enough space here. I'll have to come back to this. this example here. But what I want to do is to well, let's go ahead and say this. So let's verify. We'll come up with a solution, but let's suppose somebody's already. Let's get a new page. So I have. Okay, and this is one of the examples in the book, is to verify that this has a solution of the form. Now, what do you think it ought to be? We've got this spring and with a mass on it, and we're just giving it a pull and letting it go, and there's nothing that's going to slow it down or anything. So what should the thing look like? It has a solution of the form y equal cosine. This is a little omega t. It looks like a little w, but cosine omega t. Okay. Omega is what's called the angular frequency, and that's just kind of a standard the little Greek variable constant to use in the case. Okay, so we verify that this has a solution of that form. This is supposed to be a 0. So that means we'll need to get the derivative and the second derivative. So the derivative of cosine omega t, well, it's going to be minus omega sine little omega t. Our equation has a second derivative in it, so we need to do that. And the derivative of this is going to be minus, we already had a minus omega, but it's times another omega cosine omega t. So the second derivative is minus omega squared cosine omega t. So let's take this guy, change color here. And if I change color, I've got to change this again. So let's take this and plug in m times y double prime negative omega squared cosine omega t plus k times y cosine omega t is going to be 0. So that is negative m little omega squared cosine omega t. So we're going to solve this. So let's get let's factor out the cosine. Okay, minus m omega. You can't read that. Weird. Okay. So we'll have a solution if the cosine omega t equals 0. Okay, and that would just mean y equals 0, so we're not moving it at all. Or, which is not a very interesting solution, or when the other stuff in parentheses is equal to 0, which is minus m omega squared plus k, in other words, k minus m omega squared. I want to figure out what omega has to be. That's what I'm interested in figuring out. So k over m. Okay, this is a spring constant, and the mass is omega squared. So square root of k over m is omega squared. Is omega, excuse me. Okay, omega is the angular frequency. So it's a measure of how fast this thing is going up and down. So notice that the way this is, and I'll rewrite it over here so it's easier to see. Omega is the square root of k over n. Okay. K is large. The little omega is large as well. Now K is the spring constant. It's the stiffness. It's how much the spring pushes back. So if our spring is a really strong spring, then omega is large. This is how fast the thing oscillates. Omega measures how fast we oscillate here. So if we've got a very stiff spring, it's going to oscillate fast. Notice that if m is large, then I've got this fraction k over m, and when you make your denominator large, that makes the whole fraction small. So if m is large, omega is small. So if we have a real heavy weight on here, then it's going to tend to make the angular frequency be small. It's going to tend to make it oscillate slower. Okay, so a tougher spring, faster oscillation, a heavier weight, slower oscillation. So I'll let you catch up until I've graphed a few of these, and this is just to give you some idea. The book has this same sort of picture. If you take a cosine omega t, if we took this and let omega be the square root of k over m, if you increase k, then it's going to oscillate faster. If you increase m, then it's going to oscillate slower. Okay, so that's one of the first things we'll get out of this. Is that. Okay, so that's something you can get from the fact that there's no damping and there's no external force acting on it. Omega measures, to some extent, measures how fast it oscillates. So the larger the omega is, the faster. And it's a function of the length of the spring, the mass, and the constant of the spring. Okay. That function. Okay. Now, we still haven't. As I said, this problem was to verify that that the solution looks like that. It wasn't to actually come up with a solution on our own. It's just to verify. Let's see. There's a little more I want to do with this problem before we start working with general sort of oh, I know. I'm way out of line, I guess. Hold on. They say this whiteboard is broken, but they say the one in the next room is broken, but I work on both of them. Okay. Now the second question is a little bit different, but what effect does damping have? Well, here's a graph that shows you we'll look at this in a lot more detail, but it may, here's an example. instead of oscillating the period, the frequency uh, doesn't change, but the amplitude does. So the spring would start making big, like that. Now, if this says damping, you can't read it. If it's damped seriously, then it could be so damp that it either comes down and just kind of goes up like this and doesn't oscillate anymore, or it could be so damp that it just kind of does that sort of thing. So we'll talk about underdamped and overdamped and critically damped, things like that as well. And as far as the forcing, if you have that's right, it's a K. I was thinking of something else. You have some sort of external force. Well, you may have had the spring, you let go and it's going up and down, whatever, and then you come along and then start kicking it regularly. As I said, that's the idea of getting a bunch of little kids on the back of the school bus, jumping up and down, trying to match the frequency of the natural oscillation in the springs on the bus, and trying to nullify the amount of damping that the shock absorbers might have. Okay, but that would be an example of sometimes called a forcing function. So something might be on a regular basis hitting this, the spring is going, but something is pushing it, maybe even in a different period. But we'll really come back to the spring stuff later and do it in much greater detail. But this section was just basically to motivate the techniques we're going to be using here. Okay, so find my place here. Now, before I do anything, I want to do one of the problems. This is from page 156. Number 2, page 156. Yep. Every now and then I've done some problems like this, and it says, suppose we're looking at the case where there is no forcing function here, so we're just looking at, I've gotten out of alignment again here. This board is broken. So we're looking at this equation here, but with the forcing function being 0. So okay. So we want to do some verification here. So in this first part, we want to show that if we have a solution, then multiplying by a constant still gives us a solution. Which is just a matter of taking the derivative and the first derivative and playing around with it. It's not a very hard thing to do. Let's scoot down here so we can see it a little better. Everybody in the class can see it a little better. So we know that this is true when I put y in. Is it also going to be 0 when I put c times y in? So I probably should use some other letter. Let's call this. Let me use capital letters just so I can get my little letters from the capital letters. Okay, so we've got y, then capital Y is c times little y. So the first derivative is going to be, well, derivative constant, it's just constant times that. And the second derivative, constant times the derivative, excuse me. And the second derivative then is just constant times the second derivative. So plug all these in. Okay. So plugging that into this equation, m times y double prime times c, plus b times y prime c times y prime plus k times y. We want to know, is that equal to 0? Because if it is, then that's a solution. Factor the c's out. Everything's just got a c in front of it. A common factor, I can factor that out. I have c times m times y double prime plus b times y prime plus k times y. But we know that y, little y is a solution itself. So when I factor c out of everything that's in the brackets there is just 0 because y is a solution. Okay, so if I have a solution and multiplying by 10, I still got a solution. If I've got a solution and multiplying by 14, I still got a solution, or pi over 7. So in other words, if I have a specific solution, then a more general solution would be constant times that. If x cubed is a specific solution, then a general solution would be c times x cubed. So that's where a constant might come in. Now, part B is something we're going to be pretty important too, is if you have two different solutions, then when you add them together, you've got a solution. So I'll do that on the next page, next slide. Just a second. Because I write pretty fast. So y1 and y2 are solutions separately to that. You want to show that y1 plus y2 is the solution. Easy to write, but you can see there. So you know that if you've got m times y1 double prime plus b times y1 prime plus k times y1, you get 0. If you got m times y2 double prime plus by2 prime plus ky2 equals 0, then you want to show that when you add those two things together, you get a solution. Okay, so if it's all right, I'll just drop the parenthesis t on these. We know that all the y's are functions of t. So y prime, let y be y1 plus y2. So that's a nice thing about derivatives is the sum, the derivative of the sum is the sum of the derivatives. So y is y1 plus y2, then y prime is y1 prime plus y2 prime, y double prime is the sum of the two double primes. So plug them in up here. M times the second derivative plus b times the first derivative plus k times the function. We want to know, is that equal to 0? And just multiply out and gather them all together. Okay, so if you multiply this out, I'm going to do two things at once. I'm going to multiply everything out, and I'm going to get the y1s together and the y2s together. So m times y1 double prime. Okay. From the second one, I'm going to have a b times y1 prime. The third one, I have a k times y1. From the first, I have m times y2 double prime. The second, I have a b times y2 prime. The third, I have k times y2. So the m y1 double prime and all the stuff with the y1 is 0 because we knew that y1 was a solution. And similarly, the second one with all the y2s, that's 0 because y2 is a solution. Now we're going to use these two things extensively because when we solve our equations like we had up there with the force thing, is we're going to get pieces of solutions. And we'll need to put them back into a big solution. In other words, we'll get a y1 solution and a y2 solution. So the general solution will be add those two things together. Actually, the general solution will be constant y1 plus different constant y2. Okay, and so it's about time we started working on how do you actually solve one of these rascals. So this is basically section 4.1 I just did, and I left some things out, okay, but I think you can read the rest of it and see they talk more about what the forcing function would do, but I thought I would wait a little bit until we actually had some numbers to work with here. So we're getting into section 4.2. Actually start solving things. We're working with linear second order or ODE with constant coefficients. Okay. Of course, remember y is going to be, think of that as being some function of t. And it doesn't necessarily have to be the spring system. It can be something else. We'll come back to springs later, but right now we just want to get the general idea. So here's what this looks like. Some constant times y double prime plus some constant times y prime plus some constant times y. Now I'm using c here because we're not necessarily looking at the spring anymore, equals some function of t. And I'm going to number these kind of like the book does, although I'm not going to put all the little equations up there they do. That's number 1. And the only restriction on this is to make this a second order. Everything else can be 0, but the coefficient of the second derivative better not be. Okay. Now, to solve something like this, we're first going to look at what happens if we take this f of t away. In other words, just look at where this function on the right hand side is just 0. We have ay double prime by prime plus cy. So we're going to generate solutions in pieces. This is going to be a fairly easy equation to solve. And once we solve it, then we're going to worry about what the f of t does to it. This is called the homogeneous form of equation 1. Now this is not homogeneous in the sense of the first order DEs we saw back on the last test, so it's a different idea. Okay. Now, that's equation 2. Yeah, I'll come back with it. We'll pull up equation 2 a bunch of times. Okay, so A, B, and C are just constants. Okay, so there's no variable things going on in there. It's just like 3y double prime minus 6y prime plus 5y equals 0. Okay. Now, if you look at this a little bit and you think about it, okay, and I probably shouldn't do this. The book does it. They just talk about it, but you don't need to write this down. I'm just writing this down to say the second derivative is just a linear combination of a function and its first derivative. In other words, the second derivative is just some number times the first derivative plus some number times the original function. In other words, these function, the first derivative and the second derivative, they all look a certain amount alike. And if you think some about some functions you have, can you come up with a function whose second derivative is just kind of a linear combination of the first and the second, first derivative and the function itself? Well, I don't want you to ponder too long on that, but exponential functions are kind of like that. When you take the first derivative, you're just going to have a constant times the original function. When you take the second derivative, you're just going to have a constant times the original function. So exponential functions are functions that now they could very well be solutions here. Because each time you take a derivative, your new function doesn't vary much from your old ones. In other words, they just vary by constants. What's the difference between the first derivative and the function? A constant. What's the difference between the second derivative and the first derivative? A constant. What's the difference between that? So exponential functions are a likely candidate for solutions. So let's do that. Suppose we let y be e to the rt. That's an r in front of that t. Let's see what it would mean to have just an ordinary exponential function. If that was what would it mean for that to be a solution? Well, y prime is just r e to the rt. Y double prime, well, you're going to pick up another factor of r. That's just r squared e to the rt. So if we plug those in, to equation 2, we have a times y prime, that's r squared e to the rt, plus b times y prime, r e to the rt, plus c times y. That would be 0. And we can factor e to the rt out. Okay, so what we've said here, shown here is that y equal e to the rt is a solution if this guy, stuff in parentheses, if ar plus br plus c equals 0. Because the e to the rt is not going to be 0. Equation 3. AR squared plus BR plus C equals 0 is called the auxiliary equation. Auxiliary 2 or 4 number 2. Okay. So we've got it down to this y equal e to the rt will be a solution. It works, that makes that equation of the homogeneous form of the equation equal to 0 if this auxiliary equation, if the coefficient of r in e to the rt satisfies the auxiliary equation. And of course we know, oops, okay. You know how to solve these guys, those quadratic formula. Work on them, and maybe we can factor, maybe not. Okay. So what I thought I'd do is a problem like this. Maybe get, I've got like, I'm on page 5 of my notes and I got 9 of them, so I don't think I'll quite get done today. Okay, so this is the, so we'll have two possible values of r. One of them is the plus the square root version of the quadratic, and the other is the minus the square root version of the quadratic, or maybe it factors, you can do them anyway. But that would give us a solution each time, and we'd use the previous problem that on the previous page to, you'd have a y1 solution and a y2 solution. Okay, so I want to do, what have I got here? Oh yeah, make sure you read examples 1 and 2 on page 158. Okay. Okay, let me do problem number 6 on page 164. And that might be about all we get done, although it's really not that. I kind of like getting into these sections now because we're going to cruise a little faster, and the problems aren't, some of them aren't nearly as messy as what we've had already. So we want to find the general solution to this differential equation. Y double prime minus 5y prime it's supposed to be 5 plus 6 equals 0. Okay. What we have then is we have our auxiliary equation. Let me see. The numbers here, the coefficients are A is 1, B is -5, and C is 6. Our auxiliary, okay, the general solutions are going to involve e to the RT type things. That's supposed to be R. So our auxiliary equation is going to have the variable R in it. It's going to be A times R squared, B times R plus C. So it's A times R squared, B times R plus C equals 0. And fortunately, I don't have to quadratic formula this guy. R minus 3 times R minus 2. I've got this wrong on my notes. I may never use my notes again, but I want to make sure. Okay, it's because I get a positive 6 when I multiply and -5 when I add. So we have R equals 3, R equals 2. Remember, these are e to the RT are what our solutions are like. So from the first one we get y1 is e to the 3t. From the second one we get y2 equals e to the 2t. So the general solution is, well, we've said before, we can multiply solutions by constants and we can add them together. So the general solution would be exactly that. C1 e to the 3t plus C2 e to the 2t. And you should expect two constants because we have two derivatives. If you're integrating backwards, you would have to, each time you took an antiderivative, you pick up another constant. So you're generally going to have the same number of constants as you have derivatives. Okay. So as I said, once we get into this stuff, it doesn't take long to solve some of these problems. Now, let's see. I'll do that. guess I can do a little more. What we're going to have to deal with here is several different situations. This situation, we solved a quadratic equation. We got two different solutions. But you know that when you solve a quadratic, you might have two real number solutions. One real number solution, which means our quadratic equation is actually a perfect square, or the other possibility is two complex numbers. Complex solutions. So each one of those is going to have to be handled a little bit differently. The simplest case is the one I just did. That's probably just about pretty much the simplest case is when I have two real number solutions. It's just e to the r1 t, e to the r2 t, and then put a constant in front of each one. Okay. Now, I wanted to. So, what we want to do now, the book kind of mixes things up, and I'm not real happy with the way he does it. Is he does some theory here, which the theory we're going to do applies to not just second order DEs, but also third, fourth, and fifth order ones. And I kind of wish we'd wait and do all the theory all at once. Either do that at the beginning, or else solve these and do the theory later. We're going to do a little bit of theory here first. Okay, so we want to make sure that we have all possible solutions. We also want to make sure that, we don't have any redundant solutions. What happens then if this is a perfect square? How many solutions do we get? Do we just get one, or do we get two? Okay, but they wouldn't be the same thing. I mean, if this was r minus 3 times r minus 3, you wouldn't have e to the 3t and another e to the 3t. So we want to make sure we get all possible solutions and no redundancy. So let's go back to our equation number 2, our homogeneous DE. I'm sorry. Still thinking about it. Hit the wrong thing on a smart board, all kinds of stuff happens. Okay, so we're back to our equation 2, which was a y double plus c y prime plus cy. This is the homogeneous case here, the homogeneous part of our big DE, the first DE that had a function on the right side. Okay. First, is there a solution? One of the questions we should always ask when we face the DE is there really a solution? Just because I can write something down doesn't necessarily mean there is. And the answer to this is yes. This is what's called Theorem 1, which I'm not going to prove for any real numbers. A, and the only thing, we don't want A to be 0, but B, C, and now let's say we're going to look at initial value problems. Okay. For any real numbers, A not equal to 0, B, C, T 0, Y 0, this is a Y 1. Okay. The initial value problem, A Y double prime plus B Y prime plus C Y equals 0, where the value of the function at t0 is y0, and the value of its derivative at t0 equals y1. Okay, so any collection of constants put there, this will have as a unique solution. That works everywhere. Okay. So basically what that means is when we get a complex number solution, we don't quit. Okay, there's still going to be a real unique solution. So we'll always have a nice unique solution on these guys. Second order homogeneous DE with constant coefficients. Okay, so if we were going to get our solution in pieces like we did before, we'll have an R1 and an R2 maybe. And then we need to put them together. We want to make sure that there isn't any duplicates here. Okay, so here's where we put in some definitions, and I'd almost wish you'd wait on these definitions. Okay, we're going to have two functions. Are linearly independent if. Now, if you've had differential equations, we're going to be using some of the same terms in this section as you've seen in differential equations. But two functions are linearly independent if one is not a constant multiple of another. Now, generally, we'll be working with more than two functions, in which case linearly independent is a little bit more interesting concept. If you just got two of them, then it's not too hard at all to see if things are linearly independent. Okay. Now, here's a theorem that I'm not going to prove. It says if y1 and y2 are two solutions to this equation at the top of the board that are linearly independent, then there are unique constants C1 and C2 so that C1 times Y1 2 times Y2 solves the initial value problem. Now I should have put this is called equation 10. So I left out a few equations. So in other words, if you can think of some equation here, any equation you can think of that satisfies this, we're going to have solutions, a unique solution. How do you find it? Well, if I can generate two linearly independent solutions, then I'll know I'll be able to find constants that solve that. Okay, so what we're going to deal with next time is spending a little time talking about how you guarantee that some things are linearly independent. There's a lemma that I'm not going to do that's in the book, but I'm actually going to do one of the, I'll talk a little bit about one of the exercises, which is kind of a different way to get to it. That's it. Now you have something to work on. You have this messy project, and I'm pretty sure I put it in Moodle, but I'll make sure now. It's so you need to go back and look at the lecture from last time, and it's due on Tuesday. Some of it is really, really messy algebra, but I think I have it broken down to where one problem does not depend upon uh, well, problem one, if you can't somehow go from no, you ought to be able to do problem 2b just using the equation from problem 1. Uh, problem number 3, you don't have to know anything about problems 1 and 2. And then they kind of put together a little bit. But I think I have it set up where even if you kind of mess up one section, you can do the others. But otherwise, I guess I won't see anybody till after break, so have a nice break. Yep, and I will get the test graded, and you look on Moodle. I'll have grades posted on Moodle sometime soon. So, bye.